Welcome. This is the fourth and final in a series of presentations designed to provide guidance on specific technical aspects of the indicator methodology. In this session, we look at Level 2 monitoring. This presentation is based on an accompanying technical guidance document which provides more detail, and this document is available on the indicator support platform. This presentation expands on the Level 2 concept as presented in the step-by-step methodology. It describes examples of Level 2 data and provides guidance on how to report Level 2 data. So what is Level 2 reporting? Level 2 is both optional and unconstrained. Level 1 reporting covers the parameters that are relevant at the global scale, whereas Level 2 goes further and provides the opportunity to report any water quality data of national or subnational relevance. Reporting at Level 2 may include any type of water quality monitoring data that are not captured by the simple physico-chemical parameter groups of Level 1. Level 2 reporting may include, for example, reporting on parameters such as heavy metals or based on alternative approaches to monitoring, such as using biological approaches. Level 1 monitoring maintains the global comparability of the indicator, and although it does provide good information, it is limited in scope and cannot represent all pressures to freshwater quality. And the impact of these pressures include oxygen depletion, salinisation, nutrient enrichment and acidification. And these are issues which are present and relevant at the global scale. Level 2 gives flexibility to countries to report beyond these simple measures and provides a mechanism to report on parameters and approaches that may match more closely the national capacity to monitor, and to focus on impacts on water quality that may be significant locally, nationally or regionally. Countries that choose to report at Level 2 will be asked to complete a questionnaire that is designed to make clear the type, the coverage and the format of the Level 2 data available. Based on the questionnaire responses, Level 2 data can be categorised according to the type and spatial coverage, and this will help inform the most suitable way to integrate Level 2 data with Level 1. So just briefly, the three options. Level 2 data may supplement existing Level 1 data by adding to the list of parameters. If the Level 2 data are available for the same water bodies as the Level 1 data, the additional parameters can be added to the water quality index and result in classification will be based on a greater parameter range. So in this example, the 5 Level 1 core parameter produces an indicator score of 85%. But if you add the Level 2 parameters, suspended solids and chlorophyll A, and you apply the same binary target-based classification method, this produces an indicator score of 75. So this is just a simple example to demonstrate how additional parameters could be added using a method to supplement and to extend the parameter range. Level 2 data may also supplement Level 1 by increasing the spatial coverage. For example, by including data for water bodies not monitored by Level 1. So in this example, there are Level 1 data from a rivers monitoring program, and there are Earth observation data which are available for lakes. And the two data streams are integrated to generate a Level 2 indicator score of much greater spatial coverage. If Level 1 and Level 2 data are available for the same water bodies, these can be integrated using a one-out, all-out approach. In this example, Level 1 data, additional parameters and biological data are available. And each data type are used to classify a water body as either good or not good, and if all of them return a positive classification, the water body is classified as good. But if any one of the three return a not good classification, the water body is classified as not good, regardless of the result of the other two. A limitation of this approach is that countries which are actively expanding their monitoring programs over time as their capacity to monitor increases, it may appear that water quality is actually degrading. In reality, the apparent degradation may simply reflect the additional monitoring effort, an effect of the more you look, the more you will find. This effect can be prevented if level 2 reporting is maintained and considered separately, and this will give a better indication of improvements or degradation in water quality over time. The robustness and simplicity of level 1 reporting ensures that any efforts to improve ambient water quality are reflected in the indicator score. Lastly, if neither of the other two methods, either supplementing or the one out all out approach, are suitable, level 2 data may be kept totally separate from level 1. The nature of some level 2 data may mean that neither of the above two approaches are suitable, so in these cases it's suggested that the level 2 data are still reported, but that they remain totally separate. These data may play an important role to help achieve Target 6.3 and Goal 6 by raising awareness of the importance of water quality, but they may not be suitable for calculating a numerical indicator score. So in the next few slides we look at examples of data that can be used for level 2 reporting. Many countries routinely collect data on parameters beyond those required for level 1. These may include physical and chemical parameters, toxic substances, or those related to pollution from activities such as agriculture or mining. The effect of the parameter on the freshwater ecosystem and human health will determine whether and how the data are integrated. General and physical and chemical parameters are best integrated by expanding the classification list, whereas parameters that are toxic are best suited to a one out all out approach, because if toxic compounds exceed their target values, this exceedance may not be apparent and picked up if all of the other parameters meet their targets, because of the 80% compliance ratio may still be met. Recent developments in information and communications technology have fueled the growth and popularity of citizen approaches to data collection. These allow data to be collected using simple kits and the accurate geolocation of the data collected with mobile devices. These citizen initiatives may lack the accuracy and precision of lab-based analyses, but have the advantage of being able to collect data at many more locations and at greater frequency than conventional monitoring programs. Currently, there are no national scale projects in operation, but shown here are some examples of ongoing initiatives, and we are working to test which have the greatest potential for Indicator 632 reporting. The method of integration will depend on the type of data collected. It may be possible to extend the spatial coverage of level 1 data by collecting data of the same water quality parameters. Alternatively, it may be more appropriate to look at different methods of integration. Untreated domestic sewage effluent is one of the most serious and prevalent forms of water pollution globally. Pathogens carried in wastewater can lead to serious health issues and contribute to high child mortality rates in many least developed countries. There are many bacterial, viral and protozoan pathogens that can be found in fresh waters. Some of these are included in routine monitoring for drinking water sources, but not necessarily in dedicated ambient water quality monitoring programs. Microbiological approaches may look for presence or absence of indicator bacteria that suggest the presence of bacteria that may be harmful to humans. Examples are thermotolerant coliforms such as E. coli, which can be used as an indicator of fecal contamination of water. Where water bodies are used directly for drinking water without treatment, inclusion of microbiological parameters is highly recommended. Combining pathogen data with level 1 should follow the one out all out approach of classification. If a water body does not meet good status due to pathogenic contamination, it should be classified as not good. There are many biological and ecological approaches to monitoring ambient water quality, but no single method has been tried and tested globally. Most have been developed for a country or region and then adapted for use in another country. When biological approaches have been established, they are often more economical to operate than those that employ techniques that measure physical and chemical characteristics of water. They are not useful for providing information on whether specific parameter target values have been exceeded or not, but they do provide a better overall assessment of water quality if implemented correctly. Many biological methods work on the principle that aquatic organisms respond to changes in their environment in measurable ways. For example, in response to poor water quality, species may not be able to survive or will move to a different location to avoid unfavourable conditions. If biological data are available at the same location as level 1 data, it is recommended to follow a one-out, all-out approach of classification. Earth observation satellite data are increasingly being used for water quality monitoring. However, they are limited to the optically detectable water quality parameters, and to date no single method has been adopted as the global standard. The technology is currently most suitable for relatively large water bodies such as lakes and very wide rivers, and because the spatial resolution available from current satellite images for global applications is not fine enough for the smaller water bodies. But given the extensive spatial and temporal coverage of current and upcoming satellite missions, satellite data could prove to be an important additional data source for monitoring large rivers and lakes in the near future. It's also important to mention that SDG Indicator 661 on freshwater ecosystem extent currently uses a satellite-based Earth observation method to provide a global data set on water quality. This can be used by countries if they choose to do so as part of their 632 Level 2 submission. There is a link at the bottom of this slide for further information. Mathematical models have been used to estimate pollutant concentrations and distribution for several decades. Some address pollutant fate, transport and degradation of a compound within a water body, while others model the movement of pollutants from land-based sources to a water body. Calibration and validation using real-world data are essential steps for any model to ensure that it gives an accurate representation of the situation or scenario. Models can be specific and applied to national scale for individual parameters. A good example is a map of fluoride concentrations in groundwater in India. And this was produced using a combination of real-world data and information on geology, climate and soil types. And the model predicts areas where fluoride concentration is likely to be over 1.5 milligrams per litre. And there's a link to this work at the bottom of this slide. The method used to classify water bodies as good or not good at level 1 is a simple binary method where a compliance rate of 80% qualifies a water body as good and less than 80% as not good. Countries can choose to apply more complex methods of classification that provide more information on water body status. This does not change the actual indicator score, but helps to categorise the water bodies based on their status. For example, the EU's Water Framework Directive uses 5 categories: high, good, moderate, poor and bad. And using this example, water bodies classified as either high or good would qualify as good for indicator 632. Level 1 also uses a binary approach when comparing measured values to targets. How frequently or to what degree a target is missed is not considered. This binary approach was adopted for level 1 in order to keep the method simple. For level 2, countries can choose to adopt a more complex method if they wish, such as the proximity to target, where a score of 100 indicates that the target is met, and decreasing scores indicate an increasing distance from the target. Additionally, the simple water quality index used for level 1 reporting treats each parameter group equally, with no weighting applied to any parameter group. Countries can apply more advanced classification methods, such as the one developed by the Canadian Council of Ministers of the Environment, and there's a link to this one shown here. This index calculator, which is available for download, includes measures of by how far a parameter misses its target, how many times the target is missed, and how many parameters miss their targets for a particular monitoring site. So in summary, level 2 reporting is optional and unconstrained. It allows countries the freedom to report additional data if they have the resources available to do so. It provides countries with the facility to report the quality of their freshwaters beyond the scope possible with level 1. and it allows additional parameters or approaches to monitoring to be included that may reflect better the impacts on water quality that may be locally, nationally or regionally relevant. Lastly, Level 2 data can supplement Level 1 data either by expanding the parameter list or the spatial coverage. They may be used in a one-out, all-out approach of integration, or the third option is that they may be totally kept separate. So thank you. That's the end of this short presentation. This final slide just shows the link to the SDG Indicator 632 platform and the email address for the help desk where you can address any specific questions. Thank you.